So after a refreshing 2-week pause, welcome back to the Affiliation seminar. Today's speaker is Toni Annala, who's going to talk on Atiyah Duality and applications.
Thank you for giving me this opportunity to speak. So everything I'm going to talk about today is joint work with Mark Riva and Thom Ivasa. And I also put, we recently put a preprint on archive, and this should be the number. But you can also just Google Atiyah Duality, maybe one of our last names, and that should work as well. But sort of before getting into the details of what even Atiyah Duality means and what this talk is about, let me start by some sort of motivational kind of thing. And so let's say we have a variety, U over K, and this is going to be a smooth variety. Over a field of characteristic P. And so U is smooth, but okay, it's not going to be proper. That's why I call it U. And now for such a thing, you have many different sort of cohomological invariants you could associate to it. But there's one in particular that I want to discuss now, namely, you have the algebraic de Rham complex on U, and you can take its hypercohomology. And this is what is usually called algebraic de Rham cohomology. And I want to say there is a problem with this thing, at least for some purposes. And the problem is the cohomology groups are actually vector spaces over K, but they might be infinite dimensional. And why is this a problem? Of course, it really depends on what are you trying to do. But for example, if you're trying to do some sort of point counting, let's say you're trying to count number of points over modulo P, let's say, then you're going to apply some Frobenius, and then you're going to see what kind of matrices do you get acting on these cohomology groups, and then you want to take the trace. But if it's infinite dimensional matrices, this doesn't quite make sense. And another reason is that, okay, maybe you want to use the dimension of these groups as an invariant, but if you always just get infinities out, then your invariant is kind of sucks. You cannot really use it for anything useful. Now that situation changes a little bit if you assume that you can find a good compactification. So let's say, however, if we have something bigger, so let's say we find an X which is smooth and proper, and U is an open subvariety there, in such a way that the complement is an SNC divisor. So let me denote like this, the complement of this open embedding, and I'm going to assume this is a strict normal crossings divisor. And we are in such a situation, then we can do something slightly different. Namely, instead of looking at the algebraic de Rham cohomology of Q, we look at the sort of de Rham cohomology of X, but with logarithmic poles along this boundary component. And the nice thing about this is that these are going to be finite dimensional vector spaces. Okay. And the question I'm sort of want to ask here is that is this thing actually like an invariant of U? So let us just ignore for a moment even the fact that maybe we cannot even find a good compactification. But let's say we can find a good compactification. Is it at all clear that like this kind of like this logarithmic de Rham cohomology group doesn't depend on the choice? Like we might have more than one choice of a good compactification, and we might, I mean, this might lead to different cohomology groups. And
I think Poincaré proved something about this.
yeah,
Maybe assuming some resolution, I don't remember. This was in the.
I mean, there are many results like that, assuming resolution of singularities, but we will get results without any.
Okay.
So if you assume, let's say, if you assume a resolution of singularities and weak factorization, I think then you can prove it quite easily. I think you can also prove it with just resolution of singularities. Maybe that's a slightly more sophisticated argument.
And you probably also need in this approach the field is perfect because if you blow up regular, if the regular subschemes are not smooth, then.
Oh, right. Yeah. But yeah, for us, we don't even need that, but everything has to be smooth. Okay. And so I think it's a very good habit to sort of start a talk with a corollary. So corollary of what I'm going to talk about today. I mean, maybe I should call it really a theorem, but it's more fun to call it a corollary. You have to actually work a little bit more. And the thing is that these cohomology groups, or even the complex of this logarithmic de Rham cohomology is independent of the choice of a good projective compactification. So in other words, if you find such a good compactification where this is not only proper but also projective, then you know this independence. And I'm stating this for algebraic de Rham cohomology because it's very concrete and very easy, but actually the same result holds also for crystalline cohomology. It should also hold for Hodge cohomology. Although maybe there's some things to check, maybe still. And in fact, basically it should hold for any kind of cohomology.
So you're considering, like in characteristic 0, the terms in the spectral sequence, like the cohomology of a compactification is various in log. Spectral sequence converges to the de Rham cohomology of U, and then those things should be independent.
Right, so that is what happens in characteristic 0.
Yes.
But in positive characteristic, it certainly is not the case that you converge to the de Rham cohomology of the component. So you could start with, like, if you compactify A1 with P1, you're just gonna get.
No, it converges to this modified, to this thing with the log pole.
How do I pose in the world of filtered things?
Filtered things.
Yeah, so regard this complex as a filtered complex? Is it
With what filtration, like the weight filtration?
the Hodge?
I think you can do it for the round cohomology with Hodge filtration. I think this should be doable as well.
And the crystal, you mean cohomology of the round weight with log poles?
Yes.
And do you define it properly when the field is not perfect?
I don't know what I think.
So for the crystalline cohomology plot, the U is it just smooth over the field or any?
Smooth over the field.
Huh?
Smooth over the field.
So what was the answer to my question on?
So I think we assume perfect field for crystalline, but I don't want to comment on that. Okay.
Kind of would like to go on, but what are you defining this invariant if U does not have a good compactification?
We also define this invariant if it doesn't have good compactification, but then you don't really have an access to it.
Sorry, then are these perfect complexes?
We cannot show that.
Finitable.
Yeah, we have to find a good projective compactification to find out that it's finite dimensional.
But you
So
should
like-
expect that it's finite dimensional.
Yeah, we expect this, but we expect many things.
Sorry, can I say to which extent this was not known? So what you do is you define this invariant to make sense of this? Because it sounds like a super classical question, Sam.
Right. So I think it was known if you assume resolution of singularities.
Okay. Yeah, yeah, okay. This,
Perfect.
So it was also known for the first and last terms, right?
Wait, which last one?
Like GER0 and GER-D. The structure shape and.
Yeah, that makes sense. Thank you. I'm not gonna comment on the literature.
Saying things like that. I think the speaker should be allowed to continue.
It's fine. So the plan today, so let me just give like an outline so I can sort of explain a little bit of the structure. So I will start by explaining what is stable motivic cohomology, motivic homotopy theory.
There is a geometric approach by refined okay, it's another approach.
And so this is,
Let's see if you make it a second.
this is not in the sense of like Fabian Morel and Wygotsky, but it's going to be without A1 invariance. Without A1 invariance. So it's stable motivic homotopy theory without A1 invariance. And the second thing, okay, I have Atiyah Duality in the title, so maybe I should explain what it means. So yeah, that's part 2. And the third thing really sort of gaps or like brings together like these sort of logarithmic theories and Atiyah duality. And this is a certain like operation that we call A1 co-localization. Which is a gadget of turning a cohomology theory in algebraic geometry into an A1 invariant cohomology theory in a very interesting way. Okay. So let me start with the first part, the stable motivic homotopy theory. And now, so the thing I sort of want to lead with is that not all cohomology theories are A1 invariant. Meaning that, okay, I'm gonna denote a random, like just an arbitrary cohomology theory now by H. And what this means is that in general, if H is some cohomology theory, then in general, the cohomology of X is not the same as the cohomology of a fine line over X. So for example, for algebraic Durand cohomology, this would fail horribly. However, And now I'm gonna make a statement that's not maybe 100% mathematical. So projective bundle formula. No, that's a mathematical statement. So, okay, it essentially always holds. And I don't want to make this into a mathematical statement, and strictly speaking, it's also false, but
When you study flat homology,
yeah, exactly. Yeah. Let's. But for example, for algebraic round cohomology and crystalline cohomology, you certainly have projective bundle formula. So maybe the better thing to say is that it holds in much greater generality.
for symptomic, it doesn't.
It holds for symptomic. You have to take these twists.
Okay.
So you have to, like, quite often you have to build these bi-graded cohomology theories, and then you start getting projective bundle formula. And what is projective bundle formula? It just means that we can, so that we understand the cohomology of projective space in terms of the cohomology of the base. So I'm not gonna write the precise formula here. Usually there's like a degree shifts and whatnot here. But simply speaking, as an abelian group, the cohomology of the projective space is going to be given by n+1 copies of the cohomology of X. Okay. And so the idea of stable motivic homotopy theory that me and Marco Juha and Rione Ivasa have been pursuing is to encompass like all cohomology theories that have projective bundle formula. Of say schemes that represents cohomology theories satisfying projective bundle formula. And again, this is, you cannot really directly make a definition like this. So more precisely, what we do is as follows. So first of all, we will fix a base scheme S. And this can be arbitrarily bad scheme, could be even a derived scheme. But we don't make any assumptions on the singularities or whatever of that object. And as sort of a preliminary notion, we define this sort of category of sort of, well, certain kinds of free sheaves over S. And by definition, what this kind of thing is going to be Nisnevich sheaves of spectra on smooth schemes over S. So Nisnevich sheaf explains this thing here, this decoration is. But then we have this other part, SPU. So they are not only Nisnevich sheaves of spectra, but they also satisfy smooth blow-up excision. which I am gonna explain next. But I mean, how you would sort of maybe think about this is that in motivic A1 homotopy theory, you start with some sort of motivic spaces. And this is sort of something that tries to be a little bit like that, except that you cannot actually prove anything interesting in this category. But it's a useful starting ground. So
You assume smooth is Q's and Q's. Since there are sheaves, you probably.
they're sheaves, so I think it doesn't matter.
What is smooth blow-up excision?
So the smooth law of excision. So let's say if we have some Nishnevich sheaf on SMS, so let's call it F, and if we say that it satisfies a smooth blow-up excision, if it sends a blow-up square, so we are working over a base S, and all of the things I'm going to draw here are going to be smooth over the base. So we start by a closed embedding of Z going to X. We blow up. And we get the blow up square like this. Is the exceptional divisor. And now F satisfies smooth blow up excision if it sends this one into a Cartesian square of spectra.
In an homotopy Cartesian.
Yes, homotopy Cartesian square of spectra. So in some sense, we're saying that we know what happened, or we can, the cohomology of something changes in a very controllable fashion when you blow something smooth. And you get, I mean, the sort of in practice meaning of this Cartesian, homotopy Cartesian square is that you get some sort of Mayer-Vietoris like looking sequence on the homotopy groups. Okay, and for simplicity, let me just denote this thing by this sort of curly key. And so we have a couple of ways to sort of map or consider geometric objects in this category P. So first of all, every smooth scheme over S represents a pre-sheaf, and in particular Nishnevich sheaf. And then there's a way to enforce it to satisfy this blow-up excision as well. And this thing we call, like a free object, we call X plus, meaning that it's like the suspension spectrum of the sort of, you adjoin a free base. So this is like the free object generated by X. This is the notation we use is just to keep it in line with stable homotopy theory. But there's also a pointed version. So a point for a smooth thing over X is a map from S to your thing. And then we also have a map like this, which sends X with a point to the pole fiber of these things. And usually this will be called just by X because we have not sort of adjoined the free base point. But this is just a sort of notation to keep things simple.
So in some sense, the X plus is not not topology. You just take X of S, adjoin the base point, which is discrete deterministic suspension. And or whatever.
Yeah, so I wanted to ask you there topology, which makes everything
Just add this square.
well, you could take the smooth
CH
CH topology, and that would include all of these things.
The same thing.
I guess it should be. Eldon says, yeah, and it's recorded now. Anyway, there's also a symmetric monoidal structure.
So how much you have to shift to guarantee this? You have to shift to impose everything. You start with X plus and you impose.
So if you start with like the pre-sheaf represented by X, that will automatically be a Mishnevich sheaf, right? Because Mishnevich is less fine than at half.
Yes.
But then you have to make these blow-up excisions work out, and that you have to enforce. But also you have to make it take values in suspension spectra, so, or the spectra, so then there's things you have to do. And well, I don't want to sort of get into the details. But this thing has a symmetric monoidal structure, which basically, by definition, is that it extends this kind of thing. But if you have sort of two smooth varieties, you take the sort of suspension spectra of them, and what you should get is the product. And this product really means the fiber product over S, but just to simplify the notation, I'm gonna drop S out of the picture. Okay. And now we're sort of finally ready to make the definition of our stable motivic homotopy category over S. And this we call MS. This comes from motivic spectra. So that's the reasoning for this name. And quite simply, we start with this category P, and then we have a point at P1. So we take P1 with the base point at infinity, and then we invert this one in symmetric monoidal way. And what this really means is that, okay, so tensoring with this point at P1 is essentially like an algebraic geometric version of suspension. So what you're doing is you're making this sort of P1 suspension an invertible operation. And this is exactly how you pass from homotopy theory to stable homotopy theory.
It must be a bit tricky,
Yes.
just a little bit, because if you the naive definition of spectra,
Yeah, you cannot
prove the cycle on three, is
and we cannot prove that.
and
So,
this use the A1 balance
right.
reaction of GL and so on. Yeah.
So we cannot use the sort of sequential spectra. We have to use something like symmetric spectra, just because of this issue. Yeah. Maybe it's true that you can prove this cyclic, but who knows? But there always exists a nice symmetric monoidal infinity category that has a nice universal property. So you can always do that, but maybe the objects are a bit tricky to work with.
So when you invert P1, you also add all colimits after, I mean, it's.
Right, I think so, yeah. Okay, and so how would you sort of think about this category? Is that objects of MS over S are like cohomology theories on smooth schemes over S. Okay, they have to satisfy like projective bundle formula, and they have to have like Mishnevich descent. That's essentially the limitations. And then maps in this category are essentially cohomology operations. And I'm slightly lying here as well, but it doesn't really matter that much. And so let me give some examples. of cohomology theories H that are represented in this motivic, by objects in this category of motivic spectra. So first of all, you have all these sort of localizing invariants, for example, K theory, algebraic K theory, topological Hochschild homology, TC, and so on. All of them will be representable.
Sorry, what does that statement literally mean? Like they're objects of P and then you just look at their image in MS or something else?
So there's an object in, there is an object in MS that sort of represents these cohomology theories in the sense that if you want to compute that cohomology on X, you just take basically the suspension spectrum of X in MS, and then you look at the mappings.
But is there, okay, maybe my question is, what's the precise statement in the first tilde? Like how do you go from functors and schemes to objects of MS?
This one?
I think it's not true.
It's not trivial, yeah.
Okay,
The other way around though, you can.
The other way around is easy.
just homing into things.
Yeah.
And these localizing invariants, what categories do they apply to? Each have a scheme.
So you start with like smooth things over S, and then you take the perp of that. Or I think you can also take cube co, or maybe, sorry, DP co, yeah. Oh yeah, you're right. So maybe you have to restrict to like perp. Yeah. And okay, algebraic Laurent cohomology is also an example, and so are crystalline, let's say absolute prismatic cohomology and all other prismatic cohomologies as well. And there's like a bunch of other examples as well, like for example, Hermitian K theory or algebraic cobordism, and then also like everything that was in stable A1 invariant homotopy theory, like all these étale homologic groups and let's say motivic cohomology over some regular base. So you don't have to do that. And okay, so thus far what I've told you is that we have this sort of fancy category that in which we can represent all of these sort of cohomology theories. But of course, it's a very fair question. Ask, why should you care?
Sorry, can I ask maybe a question about the first thing? So you said it's non-trivial, but what happens if you just have a homology theory, and so you say, okay, now you can construct a Nisnevich free sheaf by just evaluating this homology theory and all smooth schemes, and then you go through your construction. So maybe you need to you kind of enforce this condition to this free sheaf, then you pass to this localization.
Wait, sorry. So are you starting with the cohomology theory?
Yeah. So
or
it's a functor which takes a scheme and produces something, and I say, okay,
Right.
so it's a Nisnevich free sheaf. So then you can just apply all these constructions that you just wrote down.
So it should be an Nisnevich sheaf, and then for most cohomology theories in algebraic geometry, it satisfies this blow-up excision condition.
Yeah, right. But I mean, I'm just saying, you take this functor, and you view it as a Nisnevich sheaf, sheafify with respect to your topology, and then you pass.
Why would you?
Sorry.
Yeah, you won't have to sheafify in practice.
Okay, yeah, but I
I
mean,
think what he's doing is something like if you take an already infinity an infinity loop space, but you take infinite suspension like that. But I don't know why you are going to do this.
no, I think what he wants to do is the following. So you take something like the Duran cohomology. It takes something that's very sensible. Take the Duran cohomology. It's already an object of P.
Right.
It's a Nisnevich sheaf of spectra that satisfies blow-up excision. So it's already an object of P. Therefore, it's already an object of MS. Yes.
Right. And
Not the object you want, is it?
wait. Sorry. It's
You can take Duran cohomology.
yeah.
It's a sheaf of spectra. So it's already an object of P.
Yeah.
Therefore, it's an object of MS.
No. You have
That's
to.
not the object you want. Yes.
No, like not every object of P is an object of MS.
But if you don't want to, you have a lot that.
Oh, yeah, okay, yeah, you don't want to take the suspension. Yeah, okay. Now I understand.
Okay, great.
It's not that, like you have to like, because it satisfies projective bundle formula essentially. You basically use that to adjoin it with a structure.
It's a lift along the forgetful functor.
Yes,
That's to P.
yeah, exactly, yeah. So that's, yeah.
So what is the subtlety? So first of all, the convergent theory is not in the old sense of just convergent groups in the.
Yes, so if you have a cohomology theory, it certainly lives here,
Yes,
but this thing maps into here by taking the suspension spectrum.
yes,
And this is not the thing you want to consider. You want to find something here that sort of, there's a forgetful map from here, or sort of extracting the infinite loop space in motivic sense. So you want something that, something here that when you take the infinite loop space gives you back the original thing in P.
the infinite loop space relative to P1, you mean?
Yes, right. Okay. So we have this abstract category where everything can be represented, sort of, yeah, that's nice. But can you actually prove anything? Like, it's some sort of homotopy category. And there's really no value in it unless you can prove something interesting using it, right? And so the thing I want to talk about today is Atiyah duality. So remember, we're working over a base S, and then everything is going to be smooth over that. And let's say we have a vector bundle E on X. Now, given the vector bundle, we can construct something called the Thom spectrum of the vector bundle, which I'm going to denote by this. And if you have seen these sort of Thom spaces or Thom spectra in stable homotopy theory in algebraic topology, the construction is basically the same, maybe phrased in a slightly different way. Namely, you start with the projective compactification of this vector bundle over X, and then you contract the plane at infinity. So this is our definition on Thom spaces. And for example, one very simple example is that the Thom space of the trivial vector bundle of rank 1 is gonna be equivalent to this tensoring with P1.
So here P of E is the convention that it's the lines in E, so to speak, in order to have the right the compactification of
The lines in,
because if you use Grothendieck's notation, it will be like the compactification of the dual.
right. I think either convention will work during this talk. Maybe at some point I will have dual fronts, but it really shouldn't matter for what I said. Okay. Wait, sorry, where am I? I'm here, nice. Okay, so that's a very simple example of a Thom spectrum. Another theorem that Vilma, Mark, and I prove which is an analog of old result in topology, which was also known in A1 homotopy before. So here we have to assume that X is, well, first of all, everything is going to be smooth. But also, here it has to be projected. Okay? And then there's like basically two claims in one. So first of all, like this category of motivic spectra, you should really think of it as some sort of derived category. So it's somehow linear in some sense. And then it makes sense to talk about duals in this category. So the first claim is that, okay, if you start with something smooth projective, you get a dualizable object, a strongly dualizable object. And the second claim is that we can actually identify this object. Namely, it's going to be the Thom space over X of the negative tangent bundle. Now, I didn't explain that you can take Thom spaces of sort of the virtual vector bundles as well, but perhaps it's not too surprising because what is the Thom space of trivial line bundle? It's the same as taking P1 suspension, but this is an invertible operation by definition. So you can start seeing that sort of negative things also make sense. Like Thom spaces of negative vector bundles also make sense. So I guess sort of very sort of immediate corollary of this statement is that you recover like Poincaré duality. For cohomology theories that satisfy Kunev form. Yeah, that's nice. So what I'm saying that, okay, if you take cohomology theory that satisfies Kunev formula and then you evaluate it on a smooth projective, you get like a complex level Poincaré duality kind of statement from this result.
You need some orientability.
Yeah.
The cohomology of the Thom space should be, yeah.
Yes, that's very direct. I'm gonna ignore it. But so concrete examples would be algebraic de Rham, crystalline, prismatic, and so on. And these things were all known before, so we are not doing anything new here. But it just sort of gives a unified proof for many, many different classes. And I'm not gonna explain the proof of this statement, it's a bit tricky, but let me just comment it a little bit. So the first comment is that it uses, in an essential way, these Gisin maps constructed by Blanke. So yeah, sitting here, it's some upcoming work. So this is one very sort of essential ingredient in the proof. And the second is like how is the structure of the proof? It's basically by induction. Prove first for these projective spaces. And after you've done that, you can you sort of get it for anything that you can embed in projective spaces. So there is, you still have to work, but it's it's doable work. Okay,
And it is independent of the projective embedding.
that's true.
But can one describe it like basically like using the diagonal, once you have given maps in the diagonal in X or things like this, can you?
You can describe the sort of evaluation of like the pairing. You can describe explicitly using essentially the diagonal, yes. So the pairing from like X dual tensor X to the unit object is essentially given by Gießen map of the diagonal, and you do some shenanigans with that.
Is there any statement along those lines for X only smooth, but where you replace X plus by something chronically supported version of that?
That is a good question, but we certainly don't prove anything like that. I mean, the evaluation pairing should make sense even. Like, okay, you have a pairing, like, sorry. I don't want to say. So this Thom space over there makes sense even when X is not projected. It could not even proper, just smooth. And then you can you can always construct, in this case, the sort of geometric evaluation map. That's the Gießen map. But it's not going to be the dual. It's not going to be a perfect pairing. Okay.
Oh, the Rom homology can be infinite dimensional, so you
Yeah, that's why I
can't possibly have.
So X plus itself could not be equivalent.
There's some variant of X plus. That's this application.
I guess I get that.
Yeah, so this is how what I want to say about this A1, sorry, Atiyah duality. And let me now sort of finish by A1 co-localization. Okay, so what have we done? We have constructed this sort of category motivic spectra over S. And this generalizes something that Morel and Voivodsky did sort of 20 years ago, I guess. So this is like what we denote by SH of S. So it's like the stable A1 homotopy category over S. And now this is like a full subcategory in motivic spectra. And it's a very nice inclusion. It preserves all co-limits and it preserves all limits.
It should be also a quotient if you kill A1 in your MS.
Right.
I would bet. Okay.
It is.
Okay.
So the inclusion has two adjoints. One of them is the A1 localization. Let's denote it by L. And this is how, like, if you apply this, then you just get SH. Like, this is the usual way of making cohomology theories A1 invariant. So for example, if you start with algebraic K theory, you will get homotopy K theory. But now there's also a right adjoint in this case. And it turns out that this one will have quite interesting properties. However, there's a small technical hurdle here. So
what is the inclusion?
What is the inclusion?
Yeah.
Well,
at some point you have to check A1 invariant for something.
Right. So if you look at this P here, then inside there's all these presheaves that have also A1 invariants.
Okay.
And then both and then SH you get from the A1 invariant one by inverting P1.
The A1 local, okay, start.
Yeah.
Yeah, also.
But there's a small hurdle here, sort of a technical point, which is that this is not quite good enough for our purposes. So instead, for this argument at least, so instead what we have to do is well, you have the unit object here, which we call the A1 invariant sphere spectrum. And you look at its image here, and then you take modules over that one. And this is the biggest sheet ever, basically. So this is the A1, that's what we mean by A1 invariant sphere spectrum. And I mean, if you're not a sort of expert, then you really don't have to care about this. difference that much. But once you replace MSS with this one, you still have these adjoints. They just might be different functors now. But these are the adjoints that we have to use. And so here we have to make the following observation as regarding this functor R. And I thought I could prove it, but I probably won't. And the observation is that if X is dualizable, so for example, X is projective, I mean smooth and projective, everything is smooth, then this sort of A1 co-localized cohomology of X. So this is, you start with some cohomology theory, that's not A1 invariant, you apply this R functor.
H must be in one A1 module.
Yes, so in practice, the only difference when you use this category is to verify that things are modules over something A1 invariant. But this can be done if you're working over a regular basis for basically all things of interest.
Put your example.
Yeah.
What?
All your examples.
Like K is not gonna be one A1.
Over a regular basis, it's gonna be, and then, well, we basically care about this over fields. So. Okay. Well, I mean, at least for this application's purposes, like everything will work. And X is dualizable. Then you're gonna get the same answer on this A1 co-localized cohomology as you would from the original cohomology. So you have turned your cohomology theory into an A1 invariant cohomology theory, but in such a way that the values on smooth projective varieties remain unchanged. Okay. And this is essentially the key for sort of preaching A1 like this Atiyah duality and this sort of logarithmic cohomology theories, because you combine it with another ingredient. So Morel-Voevodsky purity.
Is it the one that used Atiyah duality or did not use it?
We use Atiyah duality to say that we have some interesting dualizable objects.
Oh, okay.
X is dualizable, Atiyah duality, okay.
Atiyah duality is true in MS.
Yes, yeah. That's what we prove. But there's Morel-Voevodsky. Purity. Which basically, so this is something in A1 homotopy theory. So, but now when we apply this R, we are in A1 homotopy theory, so we are free to use it. And it says that if you have a closed embedding of smooth things over a base, then when you collapse the complement of Z, you will get a Thom space. You get the Thom space of the normal bundle. So this is like a tubular neighborhood kind of theorem. And how you would sort of think about this is some sort of a localization.
Where is this taking place?
A1 homotopy theory. So SH, for example. I think, do you need SH? Maybe it's
unstable.
Okay, it's unstable. And so how would you think about this is like as a localization. So if you have a cohomology theory that's A1 invariant, then you get this kind of thing. That you have the cohomology of the Thom space of the normal bundle. Okay, so you really should think of this as the cohomology of Z, but shifted. And then that maps to the cohomology of X. So this is some sort of a push forward, like the Giesing map on cohomology. And then you can restrict to this open complement. And the claim is that this is a co-fiber sequence, so you get some sort of long exact localizations. And so if we combine this with our sort of construction of this RH, then whenever we have a good compactification, so let's say we have U maps to X is smooth projective, and it has an SNCD boundary, then we get a fiber sequence of this form, where in the middle you have the RH of X into there. You get some sort of cohomology of the SNC divisor, but it's not quite the cohomology of the SNC divisor. It's something you get when you glue the cohomologies of all the complements, or all the components of D together. So this is a slightly complicated object, but still something. And then,
sorry, quick question. So this R is for you to exist an abstract thing?
it is an abstract thing. It's like the right adjoint of the inclusion.
Yeah.
Okay. And this RH is your candidate for the cohomology theory.
Yes.
Of non-proper varieties.
Right, exactly. And actually, so we get a co-fiber sequence like this. And now because of this lemma here, we can basically remove the R from here and here. And this kind of data you can sort of compare with usual logarithmic cohomology theories of the log compactification. So this sort of, I mean, you have to work, but you get the corollary I started with if you work enough.
So one tries to have just the naive geometric ideas, like suppose you have two compactification, you take the product, you take the closure of the graph. So can you have like a cycle class of this in logarithmic cohomology and say that the map, here the isomorphism is defined in some very abstract way, but can you say that it is obtained by using a cycle class of the closure of the graph in a suit? I think the construction of the cycle class can be, well, also the question is, I'm not sure.
Yeah, I'm not sure.
I'm saying this, that you can verify that it is in some way like what I said.
Because if you have these two compactifications and like this fiber product, you still kind of, or sorry, you take the product and then you compactify the diagonal and then, but that might be singular.
What the
compactification of the diagonal might be singular, right?
No, but still cycle classes, at least in the smooth case, were constructed a long time ago, logarithmic. So here you need a version, no, in usual like raw and so on, but then you need the logarithmic version of this. It should probably, I'm not sure if there are papers now, but it's probably feasible. But I'm not sure completely.
Maybe. But this is what I wanted to end. Any questions?
Further questions?
Yes.
Is L symmetric monoidal?
Yes.
So the purity theorem doesn't hold in MS.
Yes, it does not. That's
Is
correct.
it the only reason why you change this MS to this mod? Or is
Yeah, if you want to obtain this kind of things. Sorry. So the purity also doesn't hold here.
okay.
So the purity holds after you apply R, but then you're in stable mode.
Okay, so the purity doesn't hold.
So purity doesn't hold, not in here and not in here.
Okay.
So you pass to here because of the proof of this lemma, which I skipped, so you cannot see why. But it's needed, at least it seems so. And conjecturally, we think we don't need it. But
If S is a field,
yeah, if S is a field or regular,
can you understand more or less everything?
no,
The kernel of L, for instance, no?
I don't think so.
And the anamorphism ring of the unit?
I don't think so.
Nothing.
We can. Yeah, we're just waving our hands and not understanding anything. Which is, I don't know what we are doing. Yeah.
So if S is not a field, if S is not smooth, okay,
Not regular.
not regular,
Uh-huh.
and then you apply, say, K theory or this motivic homology made up with methane, then what do you get if you apply R? What?
Well, but then it's a problem. Is it gonna be invariant, a module over an A1 invariant?
It's not gonna be, it's not gonna be 1A1 module, you're saying.
Maybe not. I'm not sure.
Why is that? Like, what, for example, like K theory, why is K theory not a 1A1 module if R is not, if S is not a regular scheme?
So somehow like the intuition here is that the sphere spectrum should be A1 invariant for regular things, essentially because K theory and motivic homology and all of these things are.
Yeah.
But once you're not regular, then things go wrong. And
So 1A1 is LA1 of 1.
yes.
L of 1.
But isn't it true that you can sort of base change from Z to S and then K theory will base change to and then that was
KGL will base change.
KGL.
KGL will base change.
The KH.
The KH will, yeah. Okay. So but K doesn't base change.
You can treat
No,
other. Sorry.
I'm sorry.
You can treat other example, but simple normal cross as compactification.
Sorry. So
Here you are in a situation where D is a simple normal square divisor.
right.
Do you have other example that you can treat? But you can consider.
At this moment, no. I mean, we want something that's patched up from smooth components in a nice way. And in particular, we use the fact that like all the components are smooth and all of the intersections are smooth and that kind of stuff.
At the beginning, you made the move from proper to projective. Do you know that this term is not true for proper, or do you just know how to?
So over a field of characteristic 0, we know that proper things are dualizable. I think we can also prove this formula for them, but that probably needs a bit more work. And I guess we expect it to be true even for other bases, but I mean, certainly like Poincaré duality holds for proper things over base for these cohomology theories. So something like that should be true, but really the problem is that, okay, we first prove it for Pn and then it's like an artifact of the proof in some sense.
Any further questions for Tony? If not, we thank him again.